welcome. We're going to be doing Physics 220, lab number 5, resistance and resistivity. The equipment for this lab is pretty straightforward. We just have 4 wires here. 2 of them are copper of different thicknesses. These are the copper here. And then we also have 2 unknown materials. And these wires are set up so that we are pumping some DC current through them and measuring the current of the amperage of the current that's going through here. And we have just a load resistor here, but the current is coming in, going through this wire, coming back around, and it's just kind of snaking through. So these wires are all in series, and then coming back out and into the power supply. And in order to measure the voltage across any segment of wire, we have this voltmeter here. It's measuring in millivolts, and the current's in milliamps, by the way. But we can just use these little clips to adjust the length that we're measuring the voltage over, or if we wanted to change to a different wire, we could move both of the leads over to a different wire and measure that. And that is pretty much it for the equipment for this lab. To begin the data collection, what we're going to do for this first part, which is labeled V equals IR, is we currently have the voltmeter measuring over the entire length of wire A. It's one of the copper wires. And so wire A measuring over the full length, and we're going to try to find the resistance over this length of wire. In order to do that, we're going to vary the current that we're sending through it and then plot how the voltage changes, and then the slope of that line is going to be the resistance that we're looking for. And so right now we have we'll just start here. The current right now is at 53 milliamps, 54-ish. And the volts, this is millivolts, so it's only 1.82 millivolts. And so that's your first data point that you would want to plot on this little graph here. But let's go ahead and get you another data point by increasing the current, just an arbitrary amount, it doesn't really matter. I increased it to 107.5, maybe 3. And the voltage went up to 3.62 millivolts. So let's go ahead and increase it some more. Okay. We're now at 296. And we went all the way up to 10. So maybe that's a good upper bound. I'm going to decrease it a little bit so that we don't have to, so it's not too hard to plot. Okay, here's another data point, 230.7-ish milliamps, 7.79 millivolts. Decrease it some more. We've got 196.8 and 6.65 millivolts. Oops, went too far there. Okay, here's one. We're at 137.5 milliamps, 4.65 millivolts. And that should be enough data points for you to plot a line. I don't think it specifies exactly how many, but just by plotting those data points, trying to do your best to fit a line to it and find the slope. That should be all that you need to get the resistance over this wire A segment. For the last part here, looking at resistivity, we have followed the instructions here and set the power supply to be 100 milliamps. So this is going to be consistent for the rest of the data collection. And then right now our voltage, well actually let me show you what we're measuring over. So this is still wire A, okay? And wire A is now set to 80 centimeters because we're measuring from 0 to 80 centimeters. And so this is the first column that we're looking at. And we want to record the voltage over that segment, and here it is here. This is still millivolts, so 2.71 millivolts. And then from there, you can calculate the resistance, and then we'll go ahead and measure the diameter of the wires, and from that you can get the resistivity. But let's go ahead and fill out this row of voltage first, and then you can do the other calculations. So let's go ahead and for the next column, we're going to still use wire A, but we're shortening it. We're cutting the length in half. So we're going down to 40 centimeters instead. And we see that the voltage is now 1.36 millivolts. And so now let's go ahead and move on. We're going to be doing wire B, which again is still copper, but it is a thinner wire. And we're going to be doing 80 centimeters. Okay, so one thing you'll notice, this is 10.71 millivolts. It's negative because, if you'll remember, the current is going through here and then coming back around. And so we have you have the ground here and the positive lead here, so it's reading as negative. You don't have to write it down as negative, just take the absolute magnitude, because that's all we're really interested in here. But that is why it showed up as negative. So there's the voltage for that one. Now we're going to go ahead and move on to the unknown wires. So this is unknown C. And again, we're still measuring over 80 centimeters. And we have a voltage of 2.91 millivolts. And then let's move on to unknown wire D, which is the thinnest one. And we have quite a high voltage of 60.12 millivolts. Again, you can just take the absolute magnitude. And so that is it for that column. From there, you can calculate the resistance in each of those segments. And then in order to normalize for varying lengths and diameters, we want to find the resistivity, which is the true property of the material. And in order to do that, we already have the lengths, but we need to know the diameter so we can find the cross-sectional area of each of the wires. And so we have a pair of calipers here. I'm just going to come in, and so it's zeroed. Yep, zeroed. And I'm going to come in and just kind of pinch the wires. So this is wire A with copper, 0.81 millimeters. Wire B, the thin copper, 0.41 millimeters. Unknown C. And then unknown D. You can go ahead and, if you have trouble getting those numbers, you can just go back and pause, right? But that is it for the data collection. You should be able to estimate which, these wires, one of them is nickel and one of them is aluminum. And so by finding the resistivity and comparing it to the accepted and known value for those two materials, you should be able to classify which one's which. So thanks for watching, and good luck with your calculations.